While you were sleeping on the night of November 11th, 2025, something returned to our sky. Something that had vanished behind the most brilliant object in our solar system. Something that travelled 7 billion years through the cosmic void just to pass through our neighbourhood once, and only once. On that November morning, as dawn broke across the eastern horizon, an object that had been invisible for weeks suddenly reappeared. And here's what makes this moment impossible to ignore. We will never see it again. Not in your lifetime, not in your children's lifetime, not in the entire future history of human civilization. So before this extraordinary moment slips away, hit the like button to show you're part of this cosmic journey, and drop a comment telling me where you're listening from. Your perspective matters as we witness this rare visitor together. Think about that for a second. While you were going about your life in late October, a visitor from another star system made its closest pass by our Sun, hidden from our view by the very star that briefly captured its trajectory. Now it's back, visible again, racing away from us at 152,000 miles per hour. But here's the thing that should make you sit up and pay attention. We only have until mid-December before this object fades beyond the reach of even our most powerful telescopes. After that, it exits our solar system completely by January 2026, never to return. This isn't a comet that will swing back around in 70 years like Halley's. This is a one-time crossing, and right now, in this moment, you're living through the final chapter of a story that began billions of years ago in a solar system so distant we may never identify which star it came from. The object has a designation that sounds cold and clinical. 3I Atlas. The 3I tells you everything you need to know about how rare this is. It's only the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that strange cigar-shaped object that sparked endless debate. The second was 2I/Borisov in 2019, a comet that looked refreshingly normal compared to its predecessor. And now we have this, 3E Atlas, which on November 11th reappeared in our eastern pre-dawn sky, as predicted by astronomers, after spending weeks hidden behind the sun's glare during what astronomers call solar conjunction. Here's what happened. On October 29th, 2025, 3I Atlas reached Perihelion, its closest point to the Sun, at a distance of approximately 130 million miles. That's just inside Earth's orbital distance. For context, we're about 93 million miles from the Sun, so this object came closer to our star than we are right now. But here's where it gets interesting. Starting around October 1st, as the comet drew nearer to the Sun, its angular separation from the Sun as viewed from Earth, what astronomers call solar elongation, dropped below 30 degrees. When any celestial object gets that close to the Sun in our sky, it becomes effectively invisible to ground-based observers. The Sun's overwhelming brightness drowns out everything near it. It's like trying to spot a firefly next to a stadium floodlight. So from early October through November the 10th, 3I Atlas was there, racing through the inner solar system, but we couldn't see it. It had disappeared behind our Sun from our perspective, hidden in the solar glare during the most dramatic phase of its journey. And that's when something unexpected happened. Something that has astronomers reviewing data with intense focus and casual observers wondering if maybe, just maybe, there's more to this story than a simple comet flyby. But November 11th changed everything. The geometry shifted. Earth's position in its orbit combined with the comet's hyperbolic trajectory meant the angular separation between the Sun and 3I Atlas increased enough for the object to emerge from the solar glare. Observers with the right equipment and clear skies reported seeing it again in the constellation Sagittarius, low in the eastern sky before dawn. NASA's Planetary Science Division confirmed the reappearance. The European Space Agency's monitoring stations verified the object's position matched predictions, and suddenly what had been invisible for weeks was back, but transformed. This is your moment. Right now, as you're reading this, 3I Atlas is visible in the pre-dawn sky, moving through the constellations as it races outward from the inner solar system. Each night that passes, it moves farther from the Sun and closer to its ultimate destiny, permanent departure. You're not reading about something that happened last year or might happen next year. This is occurring now. The clock is counting down. By late December, the object will have faded to magnitude 18 or dimmer beyond the reach of amateur equipment, visible only to professional observatories. By January 2026, it crosses the threshold where even those observatories will lose track of it. And after that, it's gone, not dormant. Not in a distant orbit. Gone. Travelling through interstellar space at speeds that will carry it light years away within just a few centuries, never to be seen by human eyes again in all of human history. What I want you to do right now, before we go any deeper into what happened while this object was hidden, before we examine the strange data that emerged from those weeks of invisibility, before we explore what this visitor from another star system might tell us about the universe, is think about where you are right now. Your location on Earth matters. If you're in the northern hemisphere, you have viewing advantage. If you're near the equator, you have a narrow window. If you're in the southern hemisphere, your opportunity is limited but still possible. But wherever you are, the shared reality is this. You are alive during one of the rarest astronomical events possible. An object from another star system, billions of years old, is passing through our neighbourhood for the first and only time in human history, and you have mere weeks to witness it before it's gone forever. Comment below and tell me where you're observing from. Tell me if you're going to try to see this object in your sky. Because what's about to unfold in this story isn't just about scientific data and astronomical measurements. It's about the profound privilege of witnessing something that connects us to the deepest cosmos, something that will never happen again. But here's the question that's been keeping astronomers and curious observers up at night. What happened while 3i Atlas was hidden behind the Sun? Because when it reappeared on November 11th, something had changed. Something unexpected. Something that doesn't quite match the normal behaviour of comets. And that's where this story really begins. You need to understand something fundamental about how we see objects in space. It's not just about whether an object exists or whether it's bright enough. It's about geometry. The relationship between where you are, where the Sun is, and where the object is determines everything. And when 3i Atlas approached its closest point to the Sun in late October 2025, that geometry worked against ground-based observers in a dramatic way. Let me paint you a picture. Imagine standing on Earth, which is orbiting the Sun at about 93 million miles out. Now, imagine a comet approaching the Sun on a trajectory that brings it to 130 million miles from the Sun, closer than Mars but farther than us. As this object moves toward Perihelion, the angle between the Sun and the object as viewed from Earth gets smaller and smaller. The angle is called solar elongation, and it's measured in degrees. When solar elongation drops below about 30 degrees, you have a problem. The Sun's light dominates the sky so completely in that region that even relatively bright objects become invisible to ground-based telescopes. It's not that the object disappeared, it's that we lost the ability to see it from Earth's surface. By October 1st, 2025, 3i Atlas had already dropped below that 30-degree threshold. For the next several weeks, as it made its closest approach to the Sun on October 29th, and then began moving away on the outbound leg of its hyperbolic trajectory, ground-based observers couldn't track it. Amateur astronomers who had been following the comet since its discovery earlier in the year lost sight of it. Even professional observatories with powerful telescopes and advanced light-blocking techniques couldn't pierce the solar glare. The comet had entered what astronomers sometimes call the solar exclusion zone, a region around the Sun where Earth-based observation becomes impossible. But here's what most people don't realise. We weren't completely blind. While ground observers lost sight of 3i Atlas, space-based instruments never did. NASA operates a spacecraft called SOHO, the Solar and Heliospheric Observatory, that has been stationed at a gravitationally stable point between Earth and the Sun since 1995. SOHO carries coronagraphs, instruments specifically designed to block the Sun's disk and reveal the faint corona and any objects near the Sun. During October 2025, SOHO's LASCO coronagraph captured 3i Atlas, transiting through its field of view. The comet appeared as a small bright dot moving against the background of stars in the solar corona, tracking exactly where orbital predictions said it should be. STEREOA, another NASA mission, provided a different angle. STEREOA orbits the Sun ahead of Earth, giving it a perspective from the side rather than from our position. During the same period when we on Earth couldn't see 3i Atlas, STEREOA's cameras tracked it continuously. Think about that. While the comet was invisible to billions of people on Earth's surface, a spacecraft positioned elsewhere in the solar system watched it the entire time. And then there's GOES 19, one of the United States' newest geostationary weather satellites, which carries an instrument called CCOR-1, a chronograph primarily meant for space weather monitoring. GOES 19 happened to catch 3i Atlas passing through its field of view during perihelion as well. 3 different space-based platforms, watching from 3 different vantage points, all seeing what we couldn't. What this meant was that while ground-based astronomers waited for November 11th and the comet's re-emergence from solar glare, scientists analysing space-based data were seeing the comet in real time through its closest solar approach. They were watching it heat up as it neared the sun. They were observing changes in brightness and structure that only happen at close solar distances, and they were collecting data that would later raise serious questions about what exactly this object is and how it was responding to solar heating. You see, when a comet approaches the sun, things happen. Comets aren't solid rocks. They're mixtures of ice, dust, and frozen gases that have spent most of their existence in the deep freeze of space. When solar radiation hits a comet, those ices begin to sublimate, which means they turn directly from solid to gas without becoming liquid first. That process creates the coma, the fuzzy atmosphere around a comet's nucleus, and if enough gas is released, it can form a tail that streams away from the sun due to solar wind pressure. The closer a comet gets to the sun, the more intense this process becomes. At perihelion, when solar heating is at maximum, comets often experience their most dramatic outgassing events. Normal comets follow predictable patterns during perihelion passage. Their brightness increases as they approach the sun, peaks somewhere around closest approach, and then decreases as they move away. The rate of brightness change typically follows what astronomers call a power law relationship with distance from the sun. For most comets, brightness scales with something like the inverse cube or inverse fourth power of heliocentric distance. That's technical language for saying, when you cut the distance to the sun in half, the comet gets roughly 8 to 16 times brighter. It's predictable. It's well understood. It's been observed in thousands of comets over centuries of astronomical study. But 3i Atlas didn't follow that script exactly. When scientists examined the SOHO, STEREOA, and GOES 19 data from the October perihelion passage, they noticed something unusual in the brightness curve. The object brightened faster than expected as it approached perihelion, and based on some preliminary analyses showed brightness fluctuations that didn't perfectly match standard comet models. Now, I need to be clear here. This doesn't mean something bizarre or artificial is happening. Comets are complex, and individual objects can deviate from average behavior for entirely natural reasons. Differences in composition, nucleus rotation, jet activity, or structural integrity can all produce brightness curves that don't follow the textbook examples. But it does mean that while 3i Atlas was hidden from our view, tucked behind the sun's glare from Earth's perspective, it was undergoing changes that we're still working to fully understand. The space-based observations captured those changes in detail, but analysing that data takes time. Scientists don't just glance at an image and know what's happening. They measure light curves, calculate power law indices, compare observations across different wavelengths, and model physical processes that could explain what they're seeing. That work was underway throughout November as the comet reappeared in the morning sky, and astronomers on the ground could once again point their telescopes at it. What did they see when they looked? They saw a comet that had survived perihelion passage intact. There was no catastrophic breakup, no dramatic fragmentation into multiple pieces visible to all observers, though we'll talk more about some claims regarding that. In a moment, the object was still coherent, still moving on its predicted hyperbolic trajectory, still showing cometary activity with a visible coma. But the question of what exactly happened during those hidden weeks behind the sun, why the brightness behaved the way it did, what might have driven any anomalies in the data, whether the object experienced unusual outgassing or structural changes, those questions lingered as astronomers rushed to gather as much data as possible during the narrow window of remaining visibility. Because here's the thing you need to understand about solar conjunction. It's not just an inconvenient gap in observations. It's a critical period when comets experience their most extreme conditions, and missing that period means missing key data about how the object responds to stress. For 3i Atlas, that hidden period coincided with its closest approach to our sun, the moment of maximum heating, maximum outgassing, maximum potential for dramatic change. And we couldn't watch it directly from Earth. We had to rely on those space-based instruments with their narrow fields of view and specific monitoring capabilities. They gave us data, yes, but not the comprehensive, multi-wavelength, high-resolution follow-up that ground-based observatories could provide. Now, with the comet back in the morning sky as of November 11th, astronomers had to work fast to characterize how it emerged from that hidden period. They had to compare perihelion observations from earlier in the year with post-perihelion observations from mid-November onward. They had to look for changes in brightness, changes in coma structure, changes in spectroscopic signatures that would reveal alterations in composition or activity level. And they had to do all of this knowing that every day that passed brought the comet farther from Earth and farther from the Sun, making it dimmer and harder to study. The clock was ticking not just on your opportunity to see this object with your own eyes or your telescope. It was ticking on science's opportunity to understand what had just happened during one of the most interesting perihelion passages of an interstellar object in recorded history. That hidden period behind the Sun created a mystery that frames everything we're about to explore. It created questions about brightness and composition and structure that lead directly into the next part of this story, the part where we talk about what the data actually showed and why some of those findings have sparked intense discussion among both professional astronomers and dedicated amateur observers who've been tracking this object obsessively. Because when you hide something from view during its most dramatic moment, and then it reappears changed, people notice, people wonder, and people start asking questions that don't have easy answers. Before we go further, let's address something that's been circulating online. Some corners of the internet have speculated about artificial origins. Could this be a probe, a spacecraft, something designed rather than formed naturally? To be absolutely clear, there is no credible evidence that 3I Atlas is anything other than a natural interstellar comet. The spectroscopic data from JWST, Hubble, and ground-based observatories all confirm the presence of water ice, carbon compounds, and hydroxyl, the exact chemical signatures we'd expect from a comet no anomalous materials. No unusual radio emissions beyond natural plasma interactions. No geometric structures or propulsion signatures. The brightness surge, while unusual, fits within the realm of natural comet behavior, just at the extreme end of the spectrum. Let's talk about what the space-based observatories actually saw while 3I Atlas was hidden from ground-based view. Because this is where the story shifts from interesting astronomical event to something that demands careful attention. When Stereoa, Soho's LASCO coronagraph, and GOES 19's CCOR-1 instrument tracked 3I Atlas through its October perihelion passage, they documented something that caught scientists' attention. A brightness surge that exceeded typical comet behavior models. Now, before you jump to any conclusions, let me be absolutely clear about something. Comets are not simple objects. They're complex dynamic systems where ice composition, dust-to-gas ratios, nucleus rotation, surface features like jets, and structural variations all influence how brightness changes with distance from the Sun. Every comet is unique to some degree. Some are dusty, producing bright comas even at large distances. Others are gas-rich, brightening dramatically only when they get very close to the Sun, and volatiles start sublimating rapidly. So when I tell you that 3I Atlas showed unusual brightness behavior, I don't mean it violated the laws of physics. I mean it deviated from the average model, and that deviation suggests something specific about this object's composition or structure. Scientists measure this by looking at what's called the absolute magnitude and the heliocentric distance power law index. In simple terms, they're asking, how does the comet's brightness respond to changes in distance from the Sun? A typical comet might show a power law index around -3 to -4, meaning that when you halve the distance to the Sun, the comet gets roughly 8 to 16 times brighter. According to preliminary analyses of the space-based coronagraph data, 3I Atlas displayed a steeper brightness curve during its perihelion approach. Some assessments suggested a power law index closer to -7 or even steeper in certain phases. That's not just unusual, that's dramatic. It suggests rapid, intense outgassing or possibly sudden exposure of fresh volatiles that had been buried beneath an insulating layer of dust. It suggests the object was responding to solar heating in a way that goes beyond gentle sublimation of surface ices. Something about its structure or composition caused it to brighten fast and bright, as it neared the Sun. Now, here's where we have to be careful. Some reports circulating online and in observer communities have claimed that 3i Atlas underwent fragmentation during perihelion, that it split into multiple pieces, that its nucleus broke apart under solar stress. These claims have been discussed in various forums, and I want to address them directly. As of the data available through mid-November 2025, there has been no definitive confirmation from NASA, ESA, or any major observatory of observable fragmentation visible to all observers. The object reappeared on November 11th as a coherent comet with a coma structure consistent with a single nucleus, or at most minor structural changes not easily resolved at Earth's distance. That said, fragmentation at a scale too small to resolve from Earth-based observation is not out of the question. Comets do fragment. It happens. Sometimes a nucleus splits into 2 or 3 large pieces that drift apart over days or weeks. Other times, smaller chunks carve off the main body without producing a dramatic visible separation. The absence of obvious confirmed fragmentation doesn't mean nothing happened. It means that if something did happen, it either wasn't large-scale, wasn't easily visible given the observing geometry and the object's distance, or hasn't yet been confirmed through peer-reviewed analysis of the available data. Scientists need time to study light curves, examine high-resolution images from Hubble or other platforms, and model what could explain the observed brightness patterns. What we do know is that the brightness behavior was anomalous enough to prompt follow-up observations by major facilities. In August 2025, before perihelion, the James Webb Space Telescope observed 3i Atlas using its NIRS-PEC instrument, capturing near-infrared spectroscopy that revealed the comet's composition. That data showed the presence of water ice, carbon compounds, and dust, consistent with a comet, not an anomaly. Then, after the comet reappeared in November following perihelion, the Hubble Space Telescope conducted ultraviolet spectroscopy observations. Those observations were specifically designed to detect hydroxyl radicals, OH molecules that are a direct signature of water sublimation, and to assess the comet's outgassing activity post-perihelion. Hydroxyl detection is critical because it tells you water ice is actively sublimating. NASA's Swift Observatory, which carries UV instruments, also detected hydroxyl emissions from 3i Atlas in November 2025, confirming that the comet was still actively outgassing even after moving away from perihelion. That's normal for comets. They continue releasing gas for some time as they move outward, gradually decreasing activity as solar heating diminishes. But the intensity and spectral characteristics of that outgassing, combined with the earlier brightness surge, painted a picture of an object that experienced significant heating and responded energetically. What could cause such a dramatic brightness increase? There are several natural explanations, all rooted in well-understood comet physics. First, you could have a compositional difference. Interstellar comets formed in other solar systems, where conditions may have been different from those in our solar system's outer reaches. If 3i Atlas has a higher proportion of highly volatile ices, substances that sublimate at relatively low temperatures like carbon monoxide or methane, then approaching the Sun could trigger rapid, intense outgassing beyond what we'd expect from a more typical water-dominated comet. The steeper brightness curve would then reflect that unusual composition. Second, you could have a structural trigger. Imagine a comet nucleus covered by a layer of insulating dust. As it approaches the Sun, that dust layer heats up, but it takes time for heat to penetrate deeper. At some critical distance, thermal stress could crack that dust layer, suddenly exposing fresh ice beneath. When that ice hits sunlight directly, it sublimates explosively, producing a brightness surge as gas and dust pour into the coma. This has been observed in other comets, events called outbursts, where brightness increases sharply over hours or days, then subsides. If 3i Atlas experienced such an outburst during its hidden perihelion passage, the space-based coronagraphs would have captured the spike, but ground observers would have missed the immediate onset. Third, you could have rotational effects combined with jet activity. Comet nuclei rotate, and they're often irregular shapes with active regions, jets of gas and dust that shoot out from specific areas where ice is sublimating. If 3i Atlas's rotation brought a particularly active region into sunlight during perihelion, you'd see a brightness surge corresponding to that enhanced activity. As the comet rotated further, that region might move into shadow and brightness would drop again. From a distance, watching brightness fluctuate with rotation can create patterns that don't fit simple models. Fourth, and this is where the fragmentation speculation comes in, you could have small-scale structural disruption. Not dramatic splitting into separate comets, but surface fracturing, shedding of small chunks, or internal stress causing the nucleus to lose structural integrity slightly. If pieces of the surface crumbled away under thermal stress, that would expose more surface area, more fresh ice, and produce more outgassing. You'd see brightness increase without necessarily seeing distinct separate objects. If the fragments remained close together or were too small to resolve individually, all of these explanations are plausible. All are grounded in comet science. None require anything exotic or non-natural. But here's the thing that keeps this story interesting. We don't yet have enough data to definitively say which explanation is correct. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, is reported to be observing 3I Atlas during its perihelion passage, with detailed data expected to downlink by early 2026. That data may clarify what happened. Hubble's November UV observations will be fully analysed and likely published in scientific papers. JWST's earlier observations will be cross-referenced with post-perihelion behaviour to build a coherent picture. But all of that takes time. Science doesn't operate on the YouTube comment section timeline. It operates on the careful, methodical timeline of data analysis, peer review, and consensus building. While scientists work through that process, the object itself keeps moving. It's fading as it distances from both Earth and the Sun. The window for gathering more data is closing every single day, and that's the tension built into this story. We want answers, but the object that holds those answers is slipping away, getting dimmer, becoming harder to observe, and eventually will be beyond our reach entirely before we've fully understood what happened during those hidden weeks behind the Sun. There's something almost poetic about that. An object travels for billions of years across interstellar space, enters our solar system, experiences its most dramatic transformation during the brief period when we can't directly observe it from Earth's surface, and then races away before we can fully decode what we witnessed. It's like watching a play where the most important scene happens off stage, and you only see the actors' reactions when they walk back into view. You know something significant occurred, you have clues about what it was, but you don't have the complete picture. And maybe that's appropriate. Maybe that's the reality of observing the universe. We're not omniscient observers with perfect information and unlimited time. We're participants in a cosmos that operates on its own timeline, showing us what it wants to show us when the geometry and physics align, and leaving us to piece together the story from incomplete evidence. 3I Atlas is giving us that lesson in real time. But while the scientific story plays out over months and years of analysis, there's another story unfolding right now, one you can be part of. Because regardless of what caused the brightness surge, regardless of whether the object experienced minor fragmentation or compositional outgassing or jet activity, the fact remains. This visitor from another star system is visible in our sky right now for a limited time, and you have the chance to see it before it's gone forever. So let's talk about how you actually observe this object during its final weeks in our sky. Because knowing the story is one thing, witnessing it yourself is something entirely different. As of November 11th, 2025, when 3I Atlas reappeared from behind the Sun's glare, it became visible again in the eastern pre-dawn sky. Specifically, it was located in the constellation Sagittarius, low on the horizon in the hours before sunrise. If you're in the northern hemisphere, you had an advantage. Sagittarius rises higher above your horizon during this time of year, giving you a better viewing angle with less atmospheric interference. If you're near the equator, you can see it, but with a narrower window before dawn, light floods the sky. If you're in the southern hemisphere, depending on your exact latitude, you might have limited visibility, or might need to wait until the object moves into a more favourable position later in the month. By mid to late November, 3I Atlas had transitioned from Sagittarius into Virgo. The comet's motion across the sky reflects its real trajectory through space, moving outward from the inner solar system on its hyperbolic escape path. As November progressed into December, the object continued moving through Virgo toward Leo. By mid-December, it was positioned in or near Leo, still visible in the pre-dawn eastern sky, but progressively dimmer as its distance from both Earth and the Sun increased. Here's the critical timeline you need to understand. The comet's brightness peaks in terms of visibility were in November. During that month, it was bright enough, magnitude 12 to 14. You'll need a telescope with at least an 8-inch aperture under dark skies to spot this faint, diffuse visitor. That's not trivial equipment, but it's within the reach of serious amateur astronomers. Magnitude 12 means you need a decent telescope and reasonably dark skies, free from significant light pollution. Magnitude 14 pushes the limits of what amateurs can reliably see, even with good equipment, but it's doable under excellent conditions. But comets fade. As 3i Atlas moves away from the Sun, solar heating decreases, outgassing declines, the coma thins, and the object becomes progressively dimmer. By early December, the comet had dimmed to magnitude 14 and fainter. By mid-December, it was pushing toward magnitude 16 or 17, entering the realm where you need professional-grade equipment or exceptionally dark skies, combined with large amateur telescopes and long exposures. By late December 2025, the object is expected to fade beyond magnitude 18, at which point it's effectively invisible to amateur observation and becomes the exclusive domain of professional observatories with large apertures and sensitive CCD cameras. And then comes January 2026. That's when 3i Atlas crosses the boundary, where even professional follow-up becomes difficult. The object will be distant, faint and small, lost among countless background stars in images. Tracking it requires knowing exactly where to look and dedicating significant telescope time to capture enough photons to confirm its position and brightness. Most observatories won't prioritize that kind of follow-up once the object fades below a certain threshold because the scientific return diminishes and other targets demand attention. So for all practical purposes, January 2026 marks the end of the observation window. After that, 3i Atlas will continue its journey into interstellar space, but it will do so alone, unwatched, unrecorded, carrying whatever secrets it still holds into the dark that gives you a window. Right now, in mid to late November through mid-December 2025, if you have access to a telescope in the 8-inch aperture range or larger, if you have dark skies, if you know where to point your instrument, you can see this object. You can put photons that travelled across interstellar space, reflected off an ancient comet nucleus, through your optics and into your eye or your camera sensor. You can be one of maybe a few thousand people on Earth who will directly observe this object during its one and only pass through our solar system in all of human history. Let me give you the specific details for attempting observation. First, you need to know when to look. Pre-dawn, roughly 1 to 2 hours before sunrise. That's when the sky's dark enough that faint objects are visible, but the target is high enough above the horizon to be accessible. Second, you need to know where to look. Eastern sky, in the constellations I mentioned. Sagittarius in early November transitioning through Virgo toward Leo by December. Third, you need to know what you're looking for. Not a bright, obvious object, but a faint, diffuse smudge. A small fuzzy patch that doesn't look like a star. It won't have a dramatic tail visible in small telescopes. It won't be colourful. It will be subtle, requiring averted vision and patience. If you don't have a telescope or don't have access to sufficiently dark skies, there's an alternative, the Virtual Telescope Project. This is an online initiative run by professional and amateur astronomers who provide live streaming and recorded observations of significant astronomical events. The Virtual Telescope Project has been tracking 3i Atlas and has made observations available online, allowing people without equipment to see the comet through remotely operated telescopes. It's not the same as putting your own eye to the eyepiece, but it's a way to participate in the observation, to see the object in real time or near real time, and to be part of the global community watching this event unfold. And there is a global community. Astronomers and dedicated skywatchers around the world have been monitoring 3i Atlas since its discovery earlier in the year. They've been posting observations, sharing images, comparing notes on brightness estimates, discussing activity levels in the coma, speculating about composition based on spectroscopic data, and documenting every phase of this object's journey through our solar system. You can join that community. Comment below, share your location, tell others if you're planning to observe, ask questions, connect with people who are also watching the sky during these final weeks of visibility. December 19th, 2025 is a date to keep in mind. That's when 3i Atlas makes its closest approach to Earth. Not closest to the Sun, which was back in October, but closest to our planet specifically. The distance at closest approach is approximately 1.6 to 1.8 astronomical units, which translates to roughly 240 million kilometers, or about 150 million miles. That's still far, farther than the distance between Earth and the Sun, but it's the nearest this object will ever be to us. After December 19th, the distance increases every single day, and with increasing distance comes fading brightness. So if you're going to observe, the window between now and December 19th represents your best opportunity. After that date, the geometry works against you progressively until the object fades from view entirely. Think about the speed for a moment. 3i Atlas is travelling at approximately 152,000 miles per hour relative to the Sun as it exits the solar system. That's roughly 68 kilometers per second. At that speed, the object could cross the entire United States in less than 20 seconds. It could circle the Earth's equator in about 10 minutes. That velocity is what defines its hyperbolic orbit. It's not gravitationally bound to the Sun. It's moving too fast to be captured. It's passing through, and nothing will slow it down. Over the coming years, it will cross the outer solar system, pass beyond the orbit of Neptune, drift through the Kuiper belt, and eventually enter the vast space between stars, travelling for tens of thousands of years before it approaches another stellar system if it ever does. And you're here, right now, alive at the exact moment in all of human history when this object is close enough and bright enough to be seen. That's not an exaggeration for dramatic effect. That's literal truth. No human being before you has seen 3i Atlas because it wasn't in our sky yet. No human being after you will see it because it will be gone beyond recovery. This is the window. This is the moment. And it's closing day by day, hour by hour. What strikes me about this, beyond the science, beyond the data and the telescopes and the orbital mechanics, is the sense of connection it offers. When you observe a comet, you're seeing a relic from the early solar system, or in this case, from another solar system entirely. You're seeing material that hasn't changed significantly in billions of years, preserved in the deep freeze of space, now temporarily heated and made visible by the sun's warmth. You're looking at ice and dust that predates human civilization, that predates multicellular life on Earth, that predates Earth itself, and it's right there in your sky for a few weeks, then gone. There's a particular kind of poignancy to observing something that will never return. Most comets, even long-period ones, come back eventually. Halley's Comet returns every 76 years, so if you miss it, maybe the next generation will catch it. But hyperbolic trajectory objects like 3i Atlas don't come back. This is it. One chance. And that scarcity makes the observation feel different. It's not just looking at a comet. It's witnessing a singular event, a one-time crossing, a moment when the vast cosmos briefly brought something rare and ancient, close enough for us to notice before sweeping it away forever. So here's my challenge to you. Be part of this. Whether you observe it yourself with a telescope, whether you watch through the Virtual Telescope project, whether you simply follow the updates from observatories around the world and track the object's progress through the constellations. Be part of this, mark it in your memory. Remember that in November and December 2025, you were alive and aware during the passage of 3i Atlas, the third confirmed interstellar object ever detected, a visitor from another star system making its one and only appearance in human skies, because the story doesn't end with observation. The story extends into what this object tells us about the universe, about the space between stars, about the nature of planetary systems beyond our own. And that's where we need to go next, into the question of what 3i Atlas really is, where it came from, and what its mere existence reveals about the cosmos we inhabit. Let's talk about what it actually means for an object to be interstellar. Because that word gets thrown around, and it sounds dramatic, but the reality behind it is even more fascinating than the drama suggests. When astronomers say an object is interstellar, they mean it originated outside our solar system, not in the Kuiper belt, not in the Oort cloud, not in some distant orbit around the Sun, but in another star system entirely light years away. To confirm something is interstellar, you need to prove it's not gravitationally bound to our Sun. You do that by calculating its orbit. Every object in our solar system that's bound to the Sun moves on an elliptical orbit, a closed loop. The eccentricity of that ellipse can be very high, making it long and stretched, but it's still a closed path. An interstellar object, on the other hand, moves on a hyperbolic trajectory, an open path. It comes in from interstellar space, swings around the Sun, and goes back out into interstellar space never to return. 3I Atlas has a hyperbolic orbit. That was confirmed not long after its discovery earlier in 2025, when astronomers had gathered enough observations to calculate its trajectory precisely. The orbital eccentricity is greater than 1, which is the mathematical signature of a hyperbola. That immediately told scientists this object is not native to our solar system. It didn't form here. It formed somewhere else, was ejected from that system, either through gravitational interactions with planets or through some other dynamic process, and has been travelling through interstellar space for an unknown amount of time before entering our solar system. How long has it been travelling? This is where it gets staggering. Based on spectroscopic analysis and models of interstellar object aging, 3I Atlas is estimated to be approximately 7 billion years old. Earth is 4.5 billion years old. Our Sun is 4.6 billion years old. This comet is significantly older than our entire solar system. It formed in another stellar system around another star, at a time when the material that would eventually become our Sun, our planets, and you were still scattered as dust and gas in a nebula that hadn't collapsed yet. Think about that timeline. While 3I Atlas was already a comet, already ice and dust and volatiles, the Sun was still being born. Earth didn't exist. Mars didn't exist. Jupiter didn't exist. And this object was already out there, drifting. Where did it come from? We don't know the specific star system. Tracking an interstellar object backward to its origin is extraordinarily difficult because space is so vast and because gravitational interactions with objects along the way perturb the trajectory slightly. You can model the general direction it came from, but pinpointing the exact star system requires data precision we usually don't have. For 3I Atlas, astronomers have noted the general inbound trajectory, but identifying a specific star of origin would require more detailed analysis, and likely won't be definitive given the uncertainties involved. What we do know is composition. Thanks to observations from the James Webb Space Telescope in August 2025 using the NIRSPC instrument, scientists obtained near-infrared spectroscopy of 3I Atlas before its perihelion passage. That spectroscopy revealed the presence of water ice, carbon compounds, and dust, materials entirely consistent with comets from our own solar system. This was actually a relief for many scientists because it confirmed that interstellar comets aren't wildly exotic. They're made of the same basic building blocks we see in our comets, which makes sense. Star-forming regions produce similar materials regardless of where they are in the galaxy. Hubble Space Telescope observations in November 2025 after perihelion used ultraviolet spectroscopy to detect hydroxyl radicals, OH, which are direct evidence of water sublimation. The Swift Observatory, equipped with UV instruments, also confirmed hydroxyl emissions during November. This tells us that 3I Atlas is actively releasing water vapor as ice sublimates under solar heating, classic comet behavior. The fact that it's behaving like a comet, not like some inert rock or anomalous object, further supports its identification as a genuine comet from another star system. There's more nuance in the composition, though. Some preliminary analyses of the spectroscopic data suggested possible differences in sulfur to oxygen ratios compared to typical solar system comets. If confirmed, that would indicate subtle compositional variations reflecting different formation conditions in a different stellar nebula. These kinds of differences are scientifically valuable because they offer clues about the chemistry of planet formation around other stars. If interstellar comets show consistent compositional differences from solar system comets, we can start to build a picture of how common or variable the planet formation process is across the galaxy. Now, let's address something that's been swirling around online and in some discussions: speculation about the nature of 3I Atlas beyond it being a natural comet. Specifically, there has been discussion in some circles about whether interstellar objects like this could potentially be something other than natural, whether they could be artificial probes, defunct spacecraft from another civilization, or some other non-natural construct. This speculation was particularly loud around Oumuamua in 2017, partly because of its unusual shape, its lack of visible cometary activity at the time, and its slight acceleration that couldn't be fully explained by outgassing alone. Dr. Avi Loeb, a respected astrophysicist at Harvard, was one of the scientists who publicly entertained the possibility, however remote, that Oumuamua might be artificial or at least warranted investigation from that perspective. He has been careful to say that natural explanations are far more likely, but he argues that science shouldn't dismiss the possibility of technosignatures without consideration. Regarding 3I Atlas, there has been no public statement from Dr. Loeb or any mainstream scientists suggesting artificiality. The object shows clear cometary behaviour: outgassing, hydroxyl emission, a coma, brightness changes consistent with volatile sublimation. It looks like a comet, behaves like a comet, and spectroscopy confirms it's made of comet materials. To be absolutely clear, there is no credible evidence that 3I Atlas is anything other than a natural interstellar comet. The vast majority of the scientific community treats it as such. Any speculation to the contrary is just that: speculation, not supported by data. I mention it only because it's part of the broader conversation around interstellar objects, and transparency means acknowledging what people are discussing, even if that discussion is not scientifically grounded. What is scientifically grounded is this: 3I Atlas is the third confirmed interstellar object detected passing through our solar system. The first, 1I/Oumuamua, appeared in October 2017 and caused a sensation because it was the first time humanity definitively detected an object from another star system passing through our neighbourhood. It was small, rocky or metallic, lacked a coma, and had an elongated shape based on light curve analysis. It disappeared quickly, leaving many questions unanswered. The second, 2I/Borisov, was discovered in August 2019 and was much more straightforward. A clear comet with a coma and tail, behaving normally, giving scientists time to study it extensively. It was reassuringly ordinary, proving that interstellar comets are not all mysterious anomalies. 3I Atlas falls somewhere in between in terms of the conversation it's generated. It's clearly a comet, like Borisov, but the brightness surge during Perihelion, the hidden weeks behind the sun, and the general fascination with interstellar objects keep the story compelling. It's not controversial scientifically, but it's interesting, and the fact that we've now detected 3 interstellar objects in just 8 years suggests that these objects are relatively common in the galaxy. There are probably trillions of rogue comets, asteroids, and planetesimals drifting between the stars, ejected from their home systems during planet formation. Most pass unnoticed, too far from any star to be illuminated or detected. But occasionally, one drifts close enough to a star like our Sun, catches some sunlight, and becomes visible to civilizations equipped with telescopes. We're that civilization now. We have the technology to detect these visitors, to analyze their composition, to track their trajectories, and to add them to the catalogue of things we know exist in the universe. Every interstellar object we detect is a data point. With enough data points, we can start to answer questions like, what's the distribution of compositions among interstellar objects? How often were planets and comets ejected during the early chaos of solar system formation around other stars? Are there patterns in the objects we detect? Certain types more common than others? 3I Atlas contributes to that data set. Its water ice, carbon compounds, 7 billion year age, and hyperbolic trajectory are all pieces of information that refine our understanding of the galaxy's population of wandering objects. The European Space Agency's JUICE spacecraft, which observed 3I Atlas during Perihelion, will eventually downlink more detailed data as it continues its primary mission toward Jupiter. That data will add further resolution to what we know about the comet's behaviour during its closest solar approach. Additional analysis of Hubble and JWST observations will be published in scientific journals, peer-reviewed and incorporated into the broader scientific literature. But all of that is the long-term scientific story. The immediate visceral story is that this object is here, now, visible, and about to leave forever. And that brings us to the final, most important part of this narrative: what it means, why it matters, and what we'll never know once it's gone. So here's the question you might be asking. Why does this matter? Why should anyone care about a comet passing through the solar system, even if it is from another star system? What difference does it make to your life, to human civilization, to anything beyond the small community of astronomers and space enthusiasts tracking this object? Let me tell you why it matters. Every interstellar object we detect is a direct physical sample of another stellar system. Think about that. We cannot travel to other stars. The nearest star system, Alpha Centauri, is over 4 light-years away, which means even travelling at the speed of light, impossible with current technology, it would take more than 4 years to get there. With our current spacecraft technology, which moves at a tiny fraction of light speed, the journey would take tens of thousands of years. We can't go there. We can't reach out and touch the planets orbiting other stars, can't scoop up their comets, can't analyse their asteroids. We're confined to our solar system for the foreseeable future, except when the universe brings those other systems to us. When an interstellar object passes through, it's a free sample delivered to our doorstep. We can observe it, analyse its light, study its composition, measure its properties, and learn about the conditions in the stellar system where it formed. Without ever leaving home, 3I Atlas formed 7 billion years ago in another system, around another star, under conditions that may have been similar to or different from the early solar nebula that birthed our planets. By studying it, we're studying that system. We're learning about planet formation not just here, but there. We're gathering data about the variety and commonality of planetary building blocks across the galaxy that has profound implications. If interstellar comets all look roughly the same compositionally, if they all have water ice, carbon, similar ratios of elements, that tells us something important. The basic chemistry of planet formation is universal, or at least highly consistent across different environments in the galaxy. It means that the ingredients for planets like Earth, for oceans, for organic chemistry, for potentially life, are widespread. It means we're not a cosmic fluke, but part of a common pattern repeated countless times wherever stars and planets form. On the other hand, if interstellar objects show significant compositional diversity, if some are rich in one type of ice and poor in another, if sulfur ratios vary widely, if carbon compounds come in different forms depending on the object's origin, that tells us something equally important. Stellar systems are diverse, conditions vary, and planet formation produces a range of outcomes depending on local factors. That diversity would suggest that planetary systems might look very different from one another, which affects how we think about exoplanets, habitability, and the search for life beyond Earth. Either way, we learn. Either way, 3I Atlas, just by existing and passing through our solar system, contributes information that helps answer some of the biggest questions humanity has ever asked. Are we alone? How common are planets like ours? What are the conditions necessary for life? These aren't abstract philosophical questions, they're scientific questions, and interstellar objects provide data toward answering them. But there's another reason this matters, one that's more immediate and more humbling. 3. Atlas reminds us of our place in the cosmos. It's easy to live your entire life on Earth, surrounded by human concerns, political dramas, economic fluctuations, social media noise, and forget that we live on a small planet orbiting an average star in a galaxy containing hundreds of billions of other stars, in a universe containing hundreds of billions of other galaxies. It's easy to lose perspective. And then something like this happens. An ancient comet, older than our entire solar system, travelling for millions or billions of years across the void between stars, happens to pass close enough to our sun that we can see it for a few weeks. And then it's gone, continuing a journey that will last longer than human civilization has existed or will exist. That's perspective. That's scale. That's the universe reminding you that you're part of something unimaginably vast and old, something that operates on timescales and distances that dwarf human experience, and yet you're here, aware, capable of understanding what you're seeing, capable of calculating orbits and measuring compositions and pondering origins. You're a conscious observer in a cosmos that mostly isn't conscious, and you get to witness this that matters. That's worth paying attention to. Now let's talk about what we'll never know. Despite all the observations, all the data, all the analysis, there are questions about 3I Atlas that will remain unanswered forever. First, we will never know with certainty the exact star system it came from. We can estimate a general direction, model possible trajectories backward through time, but without perfect data, and without knowing every gravitational interaction the comet experienced over millions of years, we can't pinpoint its birthplace. Somewhere out there, orbiting some star we may or may not have catalogued, there was a planetary system where this comet formed. We'll never know which one's second, we'll never fully understand the brightness surge during Perihelion, unless the data from JUICE, Hubble and JWST provides definitive answers, and even then, there will be uncertainties. Did the object experience minor fragmentation? Did it undergo an outburst? Was the composition unusual enough to drive extreme outgassing? Science will propose models, some more convincing than others, but without having a spacecraft physically visit the comet, measure it up close, sample its material, we're interpreting from a distance. Interpretation always carries uncertainty. Third, we'll never see what happens to this object next. After it leaves our solar system in January 2026, it will travel through interstellar space for tens of thousands, or hundreds of thousands of years before it encounters another star. If it ever does, it could drift for eons without ever coming close to another stellar system. It could be captured by another star's gravity in the distant future, becoming a permanent resident of that system. It could collide with a planet, fragment in interstellar space due to impacts with dust or radiation damage, or simply persist unchanged for billions more years. We'll never know. We saw it for a few months during its brief passage through our neighbourhood, and then it disappears from human awareness permanently. That's the nature of these events, they're glimpses, fleeting windows into a universe that's mostly hidden from us by distance and time. We see what we can, learn what we can, and accept that there's much we'll never know. But here's what we do know right now. The object is still visible. As I'm writing this, as you're reading this, 3. Atlas is out there in the pre-dawn sky, fading but still detectable for those with the means to observe. The European Space Agency's JUICE spacecraft is still monitoring it, and will continue to do so through February 2026, providing additional data even after it's too faint for ground-based observation. Hubble will likely continue follow-up observations as long as the object remains bright enough to justify the telescope time. Professional observatories around the world are squeezing in observations between other projects, trying to gather as much data as possible before the comet fades beyond reach. And you can still be part of it. You can still look, you can still follow the updates from those observatories, watch as the data comes in, read the papers when they're published, track the story as it develops over the coming months, because this story doesn't end in December 2025 when the comet fades from amateur view. The scientific story continues into 2026 as data is analysed and published. The cosmic story continues indefinitely as the comet travels onward into the dark. What will the next interstellar visitor be? When will it arrive? We don't know. Oumuamua in 2017 was a surprise. Borisov in 2019 was a surprise. 3I Atlas in 2025 was a surprise. There's no schedule, no predictable pattern. These objects appear when they appear, and we detect them when our technology and sky surveys happen to catch them. As our survey capabilities improve, as we build better telescopes, launch more sophisticated monitoring systems, develop more advanced detection algorithms, we'll likely find interstellar objects more frequently. Maybe one every year or two, maybe more. Each one will tell us something new, add another data point, refine our understanding of what's out there, but 3I Atlas will always be the third. It will always be the one that passed in late 2025, the one that brightened mysteriously during Perihelion, the one that reappeared from behind the sun on November 11th and gave humanity one last chance to see it before it left forever. It will occupy a specific place in astronomical history, a specific line in the catalogue of interstellar objects, a specific memory for those who took the time to observe, to follow, to care. And that's what I want to leave you with. Not just data, not just orbital mechanics and spectroscopy and brightness curves, but the experience of witnessing something rare and ancient and transient. The experience of looking up at the sky and knowing that among the countless points of light, one of them is a traveller from another star. One of them is older than your world. One of them is about to leave and never return. The experience of being present for something that will never happen again in your lifetime, in your children's lifetimes, in many generations of human lifetimes. You're here for this. You're alive right now, in November and December 2025, during the final visible weeks of 3I Atlas. Whether you observe it with a telescope, watch through the Virtual Telescope project, or simply read the updates and follow the science, you're part of this moment. You're witnessing a chapter in humanity's ongoing exploration of the cosmos, a chapter that began millions of years ago when this comet was ejected from its home system and will end in January 2026 when it fades from our instruments and slips back into the interstellar dark. By February 2026, JUICE will have transmitted its final observations. Scientists will begin the work of synthesizing all the data, comparing pre-perihelion, and post-perihelion measurements, modelling the brightness anomaly, publishing papers in peer-reviewed journals. The story will transition from active observation to retrospective analysis. And 3i Atlas itself will be beyond the orbit of Mars, heading toward the outer solar system, unreachable, unknowable, carrying forward whatever mysteries remain unsolved. These final weeks are your opportunity. These days of December, as the comet moves through Leo and fades toward invisibility, are the last chance for anyone on Earth to capture photons from this ancient visitor. After that, it's gone. Not lost. We know where it's going. But gone from our ability to see, to study, to know. It will travel for millennia, perhaps millions of years, perhaps encountering another civilization with telescopes around another star, or perhaps drifting alone in the vast spaces between stars, never seen again by anyone. But it was seen by us, by you, in this moment. And that's something. That's worth remembering. That's worth marking in your own personal history. I was there. I was alive when 3i Atlas passed through. I saw it, or I followed it, or I learned about it. I was part of the story. And maybe, just maybe, that's the real significance. Not just what we learn about interstellar comets and planetary formation and galactic chemistry, but what we learn about ourselves, about our capacity for curiosity, our drive to understand, our ability to look at a tiny smudge of light in the pre-dawn sky and recognize it as something extraordinary, something ancient, something that connects us to the deepest reaches of space and time. So go outside. Look east before dawn, find a dark sky, bring a telescope if you have one, or find someone who does, or watch online through the Virtual Telescope Project or other live streams, or simply follow the updates from observatories. But be present, be aware, be part of this, because once it's gone forever, and you'll be able to say, I witnessed it. I was there for the last chance to see 3i Atlas, the interstellar visitor, the 7-billion-year-old comet from another star during its one and only passage through our solar system. That's not just astronomy. That's history. That's memory. That's your moment in the cosmos.